Come on. Okay. All right. So last time I showed you separation of variables for solving initial boundary value problems where the PDE and the boundary conditions have to meet certain conditions, which isn't always the case. So we're going to digress for a moment to situation of, okay, suppose you have a problem that in its current form is not suitable for separation of variables. What can be done about that? Okay. Okay. So basically, we're going to transform the problem into an equivalent one with boundary conditions that are easier to work with. So when I describe separation of variables, what I mentioned at the beginning, before I got into the method itself, is that the boundary conditions have to be homogeneous. That is, like if a boundary condition is saying that the solution u is equal to something, or its first derivative du dx is equal to something at the boundary, it must be 0 for a separation of variables to be used. So if that's not true, like suppose you have like your solution u of xt is equal to some function of t on the boundary, then that's okay. We can transform it into an equivalent problem with different boundary conditions that are homogeneous. It may or may not change the PDE. It would certainly change the initial conditions, but whatever it changes to, we can go ahead and work with it. Okay. So I'm going to step through some examples and then talk about the general case after that. So first, I'm going to assume that the boundary conditions are time independent. So we're going to give us, again, I'm going to give you a sample IBVP, or initial boundary value problem. So same PDE heat equation on some interval 0 to L. And then the boundary conditions are not homogeneous. So the solution at x equals 0, some constant k1 at the left boundary point, and the right boundary point, x equals L, it's equal to some other constant, k2. But k1 and k2 are constants. They do not depend on time. That's a time independent. And then we have initial conditions. So these three pieces together specify our IBVP. So how do we transform this problem into an equivalent one where these boundary values will be 0? So the way we do it is we actually break up the solution into two parts. So the solution little u of our original problem is broken into two terms, capital U of xt. So that's what we'll actually solve for, plus some function capital B of x that we're going to find based on the boundary conditions. So how do we define capital B of x? That's the key here. So capital B has to satisfy these original boundary conditions. So if little u satisfies these boundary conditions, and capital B satisfies the same boundary conditions, then the difference of them, capital U, will satisfy boundary conditions where these values are 0. So basically, we're causing the boundary conditions to cancel out. So capital U will be 0 on the boundary. Now, reason why capital B only depends on x rather than x and t both is that the boundary conditions do not depend on t. Therefore, capital B doesn't either. So we're just going to find some function capital B that satisfies these boundary conditions and subtract it off. Okay. So the idea is to find the simplest function, capital B, that will satisfy these. And once we do, it'll turn out that capital U will satisfy this same PDE. So if little u satisfies this PDE and capital U satisfies this PDE, then the difference of them, which is B, must satisfy it also. Because the PDE is linear. So how are we going to make that work? Well, if capital B has to satisfy this, but it doesn't depend on T. So BT is 0. Well, if BT is 0 and it satisfies this equation, then BXX is 0 also. If a function of x has a 0 second derivative, it must be linear. Because if I take any linear function, I take a second derivative, I'm going to get 0. So okay, so I'm going to add something here. Linear function b of x such that b of 0 is equal to k1 and b of L is equal to k2. Now this is just a problem of finding the equation of a line that passes through 2 points, 0 k1 and L k2. Now there's different ways we could do that. I'm actually going to use what's called Lagrange Interpolation, which those of you who've taken numerical analysis of any kind are familiar with that. So the idea is this fraction here, x minus L over 0 minus L, if I plug in x equals 0, then I get 1, because everything cancels out. If I plug in x equals 0 over here in this fraction, it'll be 0, and it goes away. And I'm left with just k1. And then if I plug in x equal L, if I plug in x equal L over here, this fraction goes away. The whole term goes away. If I plug in x equals L over here, everything cancels out and I get 1. So the result is k2. So this is how I can make a function that's equal to k1 when x is 0 and k2 when x is equal to L. Later on, I'll show how you do this more generally. This is what works in this particular case. And then what I can do is I can actually simplify this. If I expand all this out, simplify as much as I can, then this is what I get. So here too, if I plug in x equals 0, I get k1. If I plug in x equal L, this fraction cancels, becomes 1, and I get the k1's canceling, and I get k2. So this function here is a linear function that satisfies both of these conditions. So now capital U is what's left over. So what problem does it satisfy? Same PDE, 0 on the boundaries, so that's good for separation of variables. And then this is the original initial data, and you subtract off capital B of x. So this is the new initial data for this problem. But now this problem is suitable for separation of variables. So once I have capital U by separation of variables, I just add on capital B of x, and then I have a solution little u of xt of the original problem. question about what was done here? I'll make clear you don't have to use this approach, and we all know how to find the equation of a line that passes through 2 points. You can just go ahead and do that, and that would give you this equation here. This is that equation like in point slope form. Okay. And I'll do another example. This will have different boundary conditions. These will be time dependent. And notice here, okay, here we have u at x equals 0 equal to some function of t. But here we have a different boundary condition, du dx at x equals L plus a constant h times u at x equals L. So a combination of a solution and its first derivative must equal this function of t. And then we have our initial condition. So this is going to be, so similar mechanism is going to be more complicated process. Now we use the same approach, except because the boundary conditions now depend on t, this add-on function, which I'm calling capital S, that must depend on t also. So it satisfies the same boundary conditions as the original solution. So then capital U will satisfy these boundary conditions with 0 on the right-hand side. So again, we're canceling out the boundary conditions. So in other words, we subtract off from little u a function that's as simple as possible that satisfies the same boundary conditions. Therefore, the difference, capital U, will satisfy homogeneous boundary conditions where you have zeros here. Okay, so we have to keep in mind that S will now depend on T. Okay, so we like U to capital U to satisfy a similar PDE, but it won't be the same PDE because of this time dependence. So we want a function that's linear in X. It's not necessarily going to be linear in T, but it will be linear in X that will satisfy the boundary conditions. So that part's the same as before. So what do I do? So I can use this same Lagrange interpolation approach. Oh, I have a typo here. This should be, wait. Okay, actually there's not, sorry, not a typo. Okay, now, K2 is yet to be determined because this boundary condition is going to be more difficult to take into account. We're going to kick a can down the road a little bit. But we do know that at x equals 0, it must be equal to g1 of t. So if I plug in x equals 0 into both these fractions, this one will go away. This will become 1, so I have g1 of t. So the left boundary condition will be satisfied. At x equals L, this term goes away. This fraction becomes 1, and I have k2 of t. I just need to find the right k2 of t so that the boundary condition on the right side will be satisfied. So how do I do that? So what I do is I take this capital S, take a derivative with respect to x, which is this, plus h times the value of S at x equals L, which is this. So by applying the boundary condition, the right boundary condition at x equals L to capital S, I get all this just from this formula here. And that has to equal G2 of T. So now what I need to do is take this equation and solve it for K2. Because G1 and G2 are given. K2 is a function I need to find. So if I just grind through the algebra and solve this equation for K2, then this is what I get in terms of G1 and G2. So now I have capital S completely specified. Okay. So if I substitute this into here, and then I simplify as much as I can, and a fair amount of simplification does happen, then this is what I get. So this is a function that satisfies both boundary conditions, and it's a linear function of x. So now what initial boundary value problem do I solve for capital U? All right, well, first, because it's a linear function, S is a linear function, SXX is 0, so that's nice. So here's my new initial boundary value problem. It's almost the same PDE, but I have to subtract off ds dt, which was not an issue before because the function capital B, our previous example, is a function of only x, so dB dt was 0. But that's not the case here, so I have to subtract that off. Same boundary conditions, except now homogeneous, equals 0 on the right sides. And then the initial data, we subtract off capital S at t equals 0. So you got to plug in t equals 0, subtract it off, and that gives you your new initial data. This PDE is not directly suitable for separation of variables, but that's actually okay. That's something we'll learn how to handle later. As to when you have this kind of source term, there is a way to handle that so that what you can get from separation of variables can still be at least useful. So this is actually, having non-homogeneity here is easier to deal with from a separation of variables point of view than having it here. So we are moving heterogeneity or non-homogeneity from one part of a problem to another, but it still gives us an advantage. Right. Are there any questions about either of these two examples? Whoops, didn't mean to put my hand up there. I was hoping we'd have more people show up, but no. Fine. Now, those are two specific cases I talked about. I want to talk about a more general case, just to have like a general procedure you can always fall back on, or most of the time anyway. So what if you have these boundary conditions? I have some linear combination of u and ux at x equals 0 is equal to some given function of t. And then this linear combination of u and du dx at x equals L is equal to some other function of t. How do we handle that? So both the examples that I've shown you so far fall into this category for different values of alpha and beta. So you have any linear combination at the two ends. So we still find a function that is linear in x that satisfies both of these. So the idea is we have this Lagrange interpolation approach with functions k1 and k2. So if I set x equals 0, this becomes k1. If I set x equals L, this becomes k2. And we need to figure out what k1 and k2 are in terms of g1 and g2. All right, so interpolation guarantees this at least. So we need to apply these boundary conditions to S. So we need a derivative, which is just this, with respect to x. So now we apply these boundary conditions to this S. And what happens when we do that? So we have these equations equal to G1 and G2. So now I have a system of two linear equations for my unknowns K1 and K2. So I'm going to rewrite these in such a way that we can get formulas for K1 and K2. So I'm rewriting the equation so we have something times K1 plus something times K2 in the first equation. And then the same thing in the second equation, something times K1 plus something times K2. And the reason why is that allows me to rewrite the system in matrix vector form. Okay. And that's what this looks like here. I factored out a 1 over L for convenience, or just to make things less cluttered. Now I can solve this system of equations for K1 and K2 here, and since I have just a 2x2 system, I can use the formula for the inverse of a 2x2 matrix, where here I have A, B, C, and D. And that would give me formulas for K1 and K2 in terms of G1 and G2. And I've worked through all the algebra on that. Kind of a mess. Okay, so it's the inverse of this matrix times G1, G2. So then, okay. And so the inverse is worked out here. It's kind of ugly. And when I carry out this matrix vector multiplication, then this is what I get here. So I have these formulas for K1 and K2. That would work for whatever alpha 1, alpha 2, beta 1, beta 2 that you're given from your boundary conditions. So this is a very general procedure for making boundary conditions that are equal to 0. And then once that's done, then the problem that you would solve would still be this one. You subtract off ds dt, and then you also have to subtract off s of x0 from your initial data. So that part's going to be the same. But one thing to keep in mind is this denominator here is the determinant of its matrix. So you have to keep in mind that the determinant can be zero. So if this determinant is zero, then this procedure that I've shown you is not going to work. Now, I'm going to point out one case of interest where it doesn't work and explain what can be done about it. But I will tell you, this does not come back. This troublesome situation does not come up on the homework that I assigned for this. We have what are called Neumann boundary conditions, which is where you have a derivative with respect to x, and x equals 0 equaling g1, and derivative at capital L is equal to g2. Because then in the boundary conditions, the general boundary conditions that I specified up here, there's no u, there's only ux. Therefore, alpha 1 and alpha 2 are both 0. So if I plug in alpha 1 and alpha 2 both 0, we notice that everything will go away. So the determinant of that matrix will be 0. So this approach of finding a function that's linear in x will not work in this case. But I can tell you what does work. If I define v equal to ux, then we have these boundary conditions. V of 0t equals g1 of t, and v of lt equals g2 of t. So that's quite convenient that here I just replace ux with v. So now we're back in a situation that we know how to handle. So what do? We find as a linear function in x, that satisfies v's boundary conditions here. And we know how to do that because that's what I was doing in the second example, or actually it's even simpler than that. Okay, so what happens in this case is actually I can kind of use a formula. If I go back to that example, I could just use, well, actually it wouldn't be exactly the same, but I can use this formula right here, where k1 and k2 are just functions of t. All right, so that would be, so k1 and k2 would just be g1 and d2. All right, so I'll show you that in a second here. All right, so that function would do the trick. At x equals 0, I get g1. At x equal L, I get g2. Then, s of xt It's just the integral. So in other words, when you have these boundary conditions, there is no linear function in x that would satisfy these, which actually makes sense because if we have a linear function that is u, then du dx is a constant. And you're not going to have a constant function satisfy these conditions. Like if G1 and G2 happen to be the same value and a constant, we could do that, but that's the only possibility. So what we do instead is we have to be more flexible. We can find a quadratic function that satisfies these conditions because its derivative is a linear function that would satisfy these. So that's how we handle that case. All right, so here we have various ways of transforming boundary conditions that are homogeneous, which allows us to use separation of variables and related techniques to solve the new initial boundary value problem. Okay. All right, so now I can open up to questions well, about any of this or about the homework. Oh, Chelsea, I see you have a hand up.
I don't know if I missed this, but I was wondering for beta in the lateral heat equation, like the proportionality constant. I was just wondering what the units for beta, like if it had units.
Oh, okay. Wait. Okay. Oh, this is one of the variations of a heat equation.
Yeah, the lateral heat loss, I think.
Okay. Right. Okay.
Like I can infer what it is from the rest because it's part of a 4.1, but I didn't know. I didn't want to really guess on it. So I thought I'd ask.
Oh, okay. All right. Oh, wait, did this come up in one of the problems? Or
Yeah, for 4.1, I believe.
oh, not 4.1. Wait. Oh, okay. Oh, okay. First appears in 2.3. Wait.
I'm on page 46.
Okay. Dang it. It takes forever to scroll through this thing.
For the unit to work out, it had to be first second.
I didn't hear her.
Could you repeat, please?
For the units to work out, it had to be inverse seconds. So it's Celsius per second. Did y'all hear that?
Oh, yeah. Okay. All right, so if I backtrack to where that was introduced in the first place, which shows up in lesson 2. Okay. Um, all right. Actually, I don't think there's enough information to arrive. At least that's like given in textbook, for instance, to arrive at it in any way other than simply backtracking to it, knowing that both sides of the equation as a whole are supposed to be temperature per time, which had to arrive at it being 1 over second, 1 over time for that.
Thank you.
All right, sorry about that. Sorry I couldn't give a more satisfying answer, but as a mathematician, I've been trained to not care about units. Actually, some of my tests, like in calculus classes, I'd give test problems on a test involving integrals, like compute the volume of this shape. And so some students will work out the integral and get the answer of it right next to it, units cubed or something like that. It's like, I sense some snark here. Okay. Yeah, because the other parameters, like the alpha squared, the units for those are given. That's how you're able to handle those terms, but not this one. Okay. Other questions?
In lesson 2, number 4.
Okay. Lesson 2.
The solutions manual mentions that the PDE is not defined at the endpoints, forcing us to use open endpoints everywhere. And I'm not sure why.
Okay. It's really weird how this textbook has a PDE crossword at the end. It's like, what the hell is that? Okay. I'm taking a look at what they're discussing here. Oh, this is something from a solution manual as opposed to the actual book. Like,
That's correct.
Okay, so that's something I don't have. Okay. What do they say exactly? That's kind of odd. There's certainly no barrier to simply specifying the appropriate initial and boundary conditions.
They state their answer, and then they just have a parenthetical. Note that the PDE is defined inside the region 0 less than x less than 1 and 0 less than t less than infinity, since the derivatives u sub t and u sub double x are not defined on the boundaries.
Oh, I see. Okay. Yeah, so this is something that is not just for this particular problem. It's customary when stating initial boundary value problem to only have a PDE defined on the interior of whatever domain. And the reason why is if you're looking at the boundary points and you're talking about derivatives, like with respect to t, for example, they could be one-sided derivatives. So the idea is that we have if you look at the whole domain of x between 0 and L, or 0 and 1 inclusive, and then t greater than or equal to 0, each portion of the initial boundary value problem, the PDE, the initial conditions, boundary conditions, exactly one of those applies on each part of that domain, just so there's no inherent conflict. Now, they do also make a point in the problem that the boundary conditions initial data do not match up, and that's something that can happen, unfortunately. And the idea is, if they don't match up, then the initial condition that doesn't satisfy boundary conditions at t equals 0 still must satisfy them for all t greater than 0. So you get some rather freaky behavior of a solution in those cases. But yeah, so yeah, just to avoid the whole one-sided derivative question. Any other?
Number 5 from lesson 1.
Right. Okay.
Towards the end, where it's talking about how many solutions are there and how does it compare with the ODE and the number of solutions concerned. Are you, I don't know, are you looking for anything specific, I guess, or?
There's not much you can say, because how do you describe infinity? But like, number of degrees of freedom, like how many pieces of a solution are you free to set, like arbitrary constants or arbitrary functions in each case. So that gives you an idea as to how flexible one kind of solution is as opposed to another.
Okay. Because I was just looking into it and was saying they were non-comparable, but I don't know.
It varies a certain apple and oranges kind of thing, because like in one case you have arbitrary constants, and another kind of arbitrary functions.
Right.
And that's another dimension you can add to it, not just how many things you're free to set, but what are those things? Are they constants, which is certainly less flexible than functions? Because you could argue that one is a special case of the other.
Okay, so again, recap. What exactly are you?
Okay. I guess I really shouldn't say I don't care about this part of a problem, but except that's kind of true. But yeah, how many degrees of freedom each solution has? That's the main thing I'm looking for. Like how many entities are you free to tweak in each case?
Okay.
Yeah. Anything more? Going once, going twice? All right. Well, you're still welcome and encouraged to shoot me an email if you have questions. And some of you know this already from prior classes with me, but yes, homework deadlines are advisory, but again, you don't want to, but I don't want people falling too far behind. But once I have a significant enough proportion of people submitted, there's 18 in the class altogether, that's when I'll start grading them. So I'll probably be ruining this weekend by doing that, in anticipation of receiving the next ones. So you can reach me on Teams tomorrow after 4 p.m. Also, so that's true for Tuesdays and Thursdays in general. Okay, I will stop the recording now, and you can all scram.